Hello everyone. Today I am going to present my internship project titled Real-Time EV Dashboard and ADS Warning System using STM32 Blueprint. This internship introduced me to the fundamentals of embedded systems and automotive electronics. During this project, I learned how modern electric vehicles monitor sensor data, process information in real time, detect possible hazards, and display important vehicle parameters on a dashboard. Along with building this project, I also learned many important concepts such as embedded systems, ARM architecture, STM32 microcontrollers, ADC, UART communication, finite state machines, sensor interfacing, and Python dashboard development. Before building any project, we must first understand the problem. Today's electric vehicles are becoming smarter every year, but road accidents are still very common. Many accidents occur because drivers cannot see vehicles in their blind spots while changing lanes. Another common problem is rear end collision, where the driver reacts too late after an obstacle appears. Traditional dashboards also display only basic information, do not provide intelligent safety warnings. Therefore, the objective of this project is to improve driver awareness by combining an EV dashboard with ADS features that provide real-time warning. But before doing this and starting everything, the first thing that we must know what is embedded system. An embedded system is a computer designed for one specific purpose. Unlike a personal computer that performs many different tasks, an embedded system controls dedicated hardware. There are many other examples for embedded systems as well, such as washing machine, medical equipment, drones, traffic lights, modern automobiles. Our project is also an embedded system because it continuously reads sensors, processes data, and controls outputs. The objective of our projects are to design real-time EV dashboard, to implement ADS safety features, establish communication between STM32 and Python, to visualize vehicle data in real time, and to simulate an automotive embedded system before implementing it on actual hardware. During this stage, I understood that a complete embedded system consists of a sensors, a processing unit communication, and a user interface. This slide shows the complete architecture of our project. The heart of our system is STM32 Bluepill. Before using STM32, I first learned what ARM is. ARM stands for Advanced Rich Machines. ARM processes use the reduced instruction set computing or RISC architecture. Instead of executing complex instructions, ARM processors execute many simple instructions very efficiently. Because of their low consumption and high performance, ARM processors are widely used in electrical vehicles, smartphones, drones, IoT devices, and industrial automation. The STM32 Bluepill is based on ARM Cortex-M3 processor operating at 72 MHz. It contains many built-in peripherals such as GPOI, GPIO, ADC, UART, SPI, timers, and PWM. In this project, STM32 acts as a brain of the entire system. It can collect data from sensor, processes it, runs the ADAS algorithm, and sends the information to dashboard. The hardware used includes the blue pill, ultrasonic sensor, virtual potentiometer LEDs, and a buzzer. The software tools include STM32 QID, PiximLab, Python, PySerial, Matplotlib, and VSPE. STM32 CubeMX helped configure the microcontroller. SPM32 IDE was used for writing and debugging firmware. PiximLab stimulated the complete hardware environment, and VSP created virtual COM ports. Python displayed the dashboard. The workflow of our project begins with sensor acquisition. At this stage, I learned about the ADC, which is analog to digital converter. Most real world sensors generate analog voltage, however, microcontrollers understand only digital values. Therefore, the ADC converts analog voltages into digital numbers. The STM32 Blue Pill contains a 12-bit ADC. This means voltages between 0 and 3.3 volts are converted into values ranging between 0 to 4095. Our project uses ADC channels to read accelerator position, brake position, SOC, and motor temperature. After collecting sensor values, STM32 processes them and executes the ADAS logic before sending information to the dashboard. To make the program more organized, we divided software into different modules. The first is the main.c file, which initialize all the peripherals. EV-control.c file calculates vehicle speed, battery percentage, torque, and brake. The ADAS.c file performs collision warning and blind spot detection. Fault.c file detects system faults and generates warning priorities. Ultrasonic.c file measures obstacle distance. UART-shell.c file sends data to the Python dashboard. Here I also learn importance of HAL or hardware abstraction layer. Instead of programming hardware registers directly, HAL provides wide, ready-made functions such as HAL ADC start, HAL UART transmit, HAL GPIO write pin, etc. This makes embedded programming much easier and more portable and easy to understand and change for future changes. This is the pinout configuration that is of our project. This slide shows the STM32 pin configuration generated using CubeMX. GPIO pins are assigned for LEDs and ultrasonic sensors. ADC channels are configured for analog inputs. UART pins PA9 and PA10 are configured for serial communication. Timers are configured for ultrasonic timing. Using CubeMX reduced configuration errors and automatically generated initialization code. Now let's talk about ADAS features. One of the most interesting concepts I learned was the finite state machine or FSM. A finite state machine divides a program into different operating states. For example, our project states are such as save, warning, collision, and fault. Depending on sensor readings, the STM32 changes from one state to another. The project also uses three ultrasonic sensors. The front sensor detects obstacle ahead, the left sensor monitors the left blind spot, the right sensor monitors the right blind spot. The system also calculates time to collision, which estimates how quickly the vehicle will reach an obstacle based on speed and distance. The obstacle here can either be a stationary or a dynamic obstacle, like cars. This allows earlier and more intelligent warning. The actual interface that we use to show our whole project is Python dashboard. The Python dashboard provides a graphical interface for monitoring the vehicle. It displays speed, battery percentage, range, torque, motor speed, obstacle distance, blind spot warnings, and alarm messages, along with visual interpretation of how the blind spot works, how the time to collision actually working there, and how one factor is affecting the other factor. To communicate with STM32, I learned about UART. UART stands for Universal Asynchronous Receiver Transmitter. It's a serial communication protocol that uses two lines, TX for transmitting data and RX for receiving data. The STM32 continuously transmits data packets to UART at 1,15,200 baud. Python receives this packet using PySerial library and updates the dashboard in real time. The thing that actually mostly intrigued me about is what UART communication. This internship helped me understand serial communication practically. Initially, I monitored UART packets using Term. Later, I used VSP to create virtual COM ports. VSP stands for Virtual Serial Port Emulator. It creates virtual communication channels between different software applications. Finally, Python successfully received live data from STM32 and displayed it on the dashboard. This communication pipelines taught me how embedded systems exchange data with external software. Now let's see the project. Hmm. See, as you can see that my acceleration pedal is at maximum. That's why the speed is increasing gradually. Let's just make it to zero and apply brakes. Reacting to this, our speed must decrease like it's 96 kilometer per hour. Now it's 95, it's decreasing now. And we can actually see the actual change in speed through graph speed history as well. The graph actually shows that how speed is increasing and then decreasing. Here you can see that actually it's going down. It means the speed is decreasing now as we applied the brakes. Now let's make it the now let's check for all the faults. First, let's check for right blind spot, then left blind spot. See, the moment it come under the range for the right blind spot, it produced an alarm which is advisory. Same goes for left and for front collision. See, when the vehicle or obstacle is in at the front, it actually detects it and also predict the time to collision for us. During that moment, the alarm is showing critical. It means that it's likely to have it's likely that we are having an accident in this condition. Now let's make it normal again. See, TTC is now at 9.9. It means time to collision. Everything is normal now. Now let's apply, okay, apply it's full. Let's increase the motor temperature. See, the motor temperature is at 72.6 degrees Celsius. The moment it crosses the threshold, it starts to give a fault. A small warning, actually, it detected it and showed us. That's how our project is actually showing every single fault or changes that happening around our car or inside our car through this dashboard. When the accelerator potentiometer increases, the dashboard speed also increases. As you can see, the speed is increasing. Changing the battery potentiometer changes the battery percentage. Let's See here, my SOC is at maximum. Let's decrease it a bit. See, my battery is decreasing now. So just set. Moving an obstacle towards the front sensor shows the front collision, and same goes for the right and left ones. Throughout this whole project and demonstration, you would continuously transfer the live data between STM32 and Python. This shows successful integration of embedded firmware, simulation, serial communication, and desktop software. This project on paper was actually one of my first experience about the embedded systems, and during this I actually faced many challenges. During this internship, I faced several challenges. Initially, configuring multiple ultrasonic sensors correctly was difficult. UART communication also required careful debugging. I encountered COM port issues while connecting Python and VSP. Understanding timers and ADC configuration took time. Finally, integrating the Python dashboard with live serial communication required multiple debugging sessions. These challenges greatly improved my debugging and problem solving skills. In conclusion, this internship helped me to connect classroom theory with practical implementation. I learned embedded systems, ARM architecture, STM32 programming, CubeMX configuration, HAL programming, ADC, UART communication, ultrasonic sensor interfacing, finite state machines, Python programming, serial communication, dashboard development, simulation using PiximLab, and embedded debugging. Most important, most important, I learned how all concepts work together to build a complete automotive embedded system. This internship has greatly improved both my technical knowledge and my confidence in embedded systems development. Thank you. I hope this project has demonstrated both the practical implementation of the embedded automotive system and the concepts I learned during the internship.